just of how hot the thing is, how big the diameter of the star is. It's called photometry. And these are always sort of randomly designed instruments at different times with different detectors, different filters. And so one of the great problems is, how do you transform data between observatories? Well, we'll have the first observatory. We're going to have a uniform, homogeneous system all over the world and in the north and the south. And we have big telescopes and little telescopes, which nobody else has. So this is a project I'm going to personally do, which is we're going to figure this all out and sort of tie all these systems together and produce kind of a bridging photometric system that will sort of help improve the accuracy of variable star research. Okay. I think if I push the button, the network will appear. Here it comes. Okay. This is actually sort of in order of construction and arrival. There's our 8 sites. Hawaii's first, Australia's second, Sedgwick is here. No, that's not meant to be Sedgwick. Sedgwick's here. This is Chile. We will be installing Chile in May and June. This is Sutherland, South Africa. We'll be installing this fall. Then we'll get so good at it, we'll split up and we'll have 2 teams, and we'll be installing in the Canary Islands at Tenerife up here, and we'll be installing at a place called Yagaderi in Western Australia, which is north of Perth and east of Geraldton. And then we don't know schedule after that. We'll put 1 meters back at the Fox telescope. We'll put 1 meters on Maui. We get approval. And we're looking at a site in Asia. We haven't made a final decision yet, but somewhere right around here, we'll be putting a site in the Himalayas, probably at around 14,500 feet. So I may never make it there. So these are the pictures of the telescopes. This is the picture of the real thing here, the 2 meter. Now, to put this in perspective, I can walk on this platform right here. I can walk under that. The observing floor for this telescope is sort of like halfway to the first row, if you imagined it, and then it went back that way an equal amount. So the building that houses this thing is enormous. The electric bill is obscene, $3,300 a month for the electricity to run it. The structure up above it is a clamshell. It just sort of opens up in 6 sections. This thing is out in the sky. It can move real fast by normal telescope standards, so we can find things quick. And it can operate in 50-mile-an-hour winds, and the winds can vibrate the thing, and it will still track the stars properly. So it's quite an engineering marvel, and it's an enormous handful for us to run 2 of these and do everything else we do, but it's a lot of fun. It's my nemesis. When I come in the morning, my first hour is reading the logs, figuring out if it went wrong, what went wrong, and what do we have to do to fix it so I can keep coming to work without having to worry about it. And we're about, I'd say, 55 to 60% of the days I come to work and I find it did just fine, thank you very much, and then I go on to do other things. So over 5 years, we've tamed it. This is the 1 meter telescope in schematic form. Bears no resemblance to this because this telescope basically is what's called an equatorial telescope. I'll speak a little more to that. And here's our little 0.4. For those of you who may not know, I'll just quickly give the shortest tutorial in the world on telescopes. Except for very specialized things, lenses aren't used anymore. Lenses haven't been used essentially since, I don't know, 1910 or something like that, or late 1800s. There's too much color error in lenses, so you have to build these really long telescopes. And the problem with these really long telescopes is if they're not balanced properly and you grab onto them and they start moving, they might pull you way up in the air, and they're very dangerous, and lots of other problems with them. So about the end of the last century, or actually it was the century before, a guy like named Crosley, I think, contracted for one of the first reflecting telescopes where you have a glass mirror, and at that time they put silver here, and it was glass and silver that made it practical. And then almost all modern telescopes, you'll have a primary mirror down here. So the light comes down, bounces up here to a focus that's basically here, and then you put another mirror here, and you bounce the light back down. You put your instrumentation down here at the bottom where you got lots of room to do everything you want. And that's the basic idea of a Cassegrain telescope. The Cassegrain telescope itself has been around a really long time. The idea was figured out long before it was practical to make them, but that's what a telescope is, basically, when all the stuff is stripped away. So here's the 2 meter. We acquired these in 2005. We also bought the company that made them because we didn't want to acquire the telescopes and not have the intellectual property. In other words, what if we owned them and we didn't have the blueprints and we didn't have the software? And that would be a big problem. So we did that. We completed another one that was in fabrication for China. And there are 5 of these in the world, and they're all operational virtually every night. Very, very high availability now. Here's a picture of Hawaii. You can see that clamshell I told you about. Hard to put scale on this, except you can see that here's a door. Okay, here's a blockhouse full of computers and pumps and hydraulic systems. Okay, that's a 20-foot weather mast right here. So this is one big toy. And here it is open, getting warmed up and essentially ruining itself for the following night because it'll get too warm. Here's the Sedgwick telescope, the Byrne telescope out at Santa Ynez. It's a little different concept, but you can see here's an aerial of the dome in construction. This dome is the same dome we're using on our 1 meters. And here's this telescope. I don't know how to give you the scale, except here's a workbench with a 6-foot top on it. So, and you know, I don't know. When I stand here, my head is about here. So this is a fairly big toy by normal standards. This mounting was designed as a senior project by 3 students at Cal Poly San Luis Obispo. They got via contact. We said, gee, we'd like to do this senior project, and do you guys have anything that you would like to do that we would make sense for a senior project? I said, yeah, we need a telescope mounting for this telescope. So 3 years later, those engineers are still with us, completing their senior project. But it's now up and running. Here's the picture in schematic form of the 1 meter telescopes. This axis here points at the North Pole, not the Polaris. That's a star near the North Pole, but it points at the North Pole, and this thing revolves essentially at the rate of 1 revolution per stellar day. So it revolves in about 23 hours and 56 minutes. It would make a revolution. Except we don't actually turn it upside down. That would be pretty bad. But that's how you follow the stars, and then you move it in this axis here, like this, in an arc, to change the latitude or the declination of the star. So the nice thing about this telescope is one axis is barely moving, one axis is moving at a very uniform rate. It's very easy to control. So easy to control that we use exactly the same electronics, exact same motors, exact same software between this and our little 16-inch telescopes. So we get huge economies of scale. And we sort of broken the code on how to build these very exotic, fancy control systems for super cheap. There's the picture again. I really should have some pictures, but we're about 2 weeks away from putting one of these together with all the parts, including the mirror and the mirror cell. But this is coming along. If anybody wants to come out and see us, we do have one of these in a dome with a couple smaller telescopes on it. It's extremely spectacular. These things